Thank you everybody for joining us today for the latest in Engineering New Zealand's Lessons Learned seminar series. Today's session is facilitated by the New Zealand Society for Safety Engineering, who I'll talk about in a moment, but our speaker is Derek Miller from the New Zealand Occupational Hygiene Society, of whom I'll do a proper intro in a moment. Move on briefly to introduce the New Zealand Society for Safety Engineering, which is an Engineering New Zealand technical group, which has existed since 2014 with a quite broad remit in the engineering, health and safety space. We have a number of principles, which you can see here, but they basically boil down to the idea that engineers as a profession have a significant and profound impact on the health and safety of persons and animals and the environment and all sorts of things. And it's incumbent on us to be deeply aware of those duties and responsibilities. The Society has a number of roles, which essentially boil down to communicating information and expertise about safety critical engineering practice, either between various disciplines in the profession, individual engineers, or between our professional bodies and other stakeholders like WorkSafe, MB, or in certain circumstances, HASANZ, the Health and Safety Association of New Zealand, which is how I know Derek and how he wound up getting drafted in for this presentation. So I'll move on to introduce Derek. We're very, very pleased that Derek was willing to deliver this session for us. Derek is a fellow of the New Zealand Occupational Hygiene Society and currently the president-elect of that group. He has many years experience across occupational hygiene and is particularly passionate about local exhaust ventilation. Pretty much the first time I met you, Derek, you got in my ear about LEV design by engineers, and you've been in my ear ever since. So when you were having a go at me earlier this year about LEV and Engineering New Zealand wanted us to put on a Lessons Learned seminar, I thought I'll just put the two and two together and get out of the way. And here we are. So we're very pleased to have you here with us. So just so everybody's aware, occupational hygiene is not necessarily a professional discipline that all engineers have encountered before. So just for the sake of some context, an occupational hygienist is a professional who works in primarily the occupational health space and is concerned with prevention of harm to people resulting from contaminants, dusts, chemicals, toxins, the things that can cause cumulative harm, chemical exposures, etc. At the very high level, that's what an occupational hygienist is. They're not here to tell us how to wash our hands. They're here to tell us how to not gas people, which is the main theme of today's session, which is focused on local exhaust ventilation. So with that, without any further ado, I will hand over to you, Derek, to kick off, and I'll jump back in at the end to MC the questions. So thank you again for today's session.
No, thanks for having me, Joe. It's a pleasure. Thanks for the introduction. I won't get my head through the door after this. Okay, good afternoon, everybody. As Joe says, I'm Derek Miller. I'm a certified occupational hygienist and a fellow of the New Zealand Occupational Hygiene Society. And one of the few loves of my life is local exhaust ventilation. And that's what we're going to talk about today. We'll run through a little introduction about it, then we'll have a chat about some of the common issues we see with LEV, then we'll talk about how can we avoid them into the future, and then as Joe says, we'll finish off with some questions and answers. So let's get stuck in. Work-related health. Why is LEV important? Well, LEV is a control, and when you look at the stats from WorkSafe New Zealand, every year 750 to 900 people are estimated to die from a work-related health issue, and 5,000 to 6,000 can be hospitalised each year. When you think about it, that is a lot of people, and we concentrate a lot on safety, but often we miss these other things. The difference between the health issues is some of these will not show for 10 to 15 years after a person's exposure. So we have to get it right at the start. Really, we're going to look at one aspect of that area today. And it says, when you look at the actual numbers, we concentrate a lot on safety, particularly through health and safety by design, etc. But you're 15 times more likely to die from a work-related disease than from a workplace accident. And yet all the publicity that we see in the news, etc., tends to be on the accidents. So what is a ventilation system? Well, it's a lot more complex than this, as you probably all know, but I've broken it down into 3 basic categories of interest here. We've got the HVAC systems, and that works around thermal comfort, acceptable indoor air quality, removing body odours, foul odours, etc. And it helps us to work, actually, if it's done properly. And that's an important area, particularly going into the future with things like climate change and the increase in temperatures. Then when we start looking at control, now HVAC is not a control system. When we come into controls or for contaminants, etc., we look at dilution ventilation and local exhaust ventilation systems. Dilution we won't cover today, but I thought it important to point out it tends to be where we ventilate the entire workplace. This is not HVAC. This is specially designed to do it and to make sure all the air is changed. So as hygienists, we don't use air changes per hour. When we're looking at control, we are working purely in meters per second, laminar flows and other areas, not in air changes. Today, we're going to concentrate on local exhaust ventilation. Notice the difference in it. We're not ventilating the whole workplace. We are trying to capture the contaminant at its actual source as it is released. Then we entrain it into the ducting system. As it goes through the duct system, an LEV will make sure that contaminant doesn't settle out and cause problems with the ventilation system and eventually come out to the baghouse or whatever type of filtration system we've got in place, precipitators, etc. And then we'll have fresh air going back out. So an LEV system is much more than just moving some air. There's a lot to be taken into account. And it's important because when we actually look at the leading causes of death in workplaces from ill health, they tend to be cancers and respiratory diseases. And a lot of people, as we saw with the numbers before, are disabled by these conditions. They become unable to work. They become a burden on the families to a degree. And a lot of them will develop the diseases because they breathe in too much dust, fumes, or other airborne contaminants at the work. So we need to control it. This is where LEV is so important. And we're looking at the woodworking industry, welding, paint spraying, stone masonry, engineering, foundry work, and many other occupations, including a lot of the green ones that are coming into the job markets now. So, common issues. If I look at my experience here in New Zealand over the past 15 years, roughly 90%, just over 90% of all systems I have looked at for LEV fail to effectively control the hazards. If you go overseas and look at data, then we take the UK, for example. They've done a fair bit of work around this area, and they have similar problems. They have discovered that only 24% of companies that have invested in installing an LEV system are actually effectively controlling the hazards. That means 76% of systems installed in the UK and paid for were a waste of money. They're not controlling. So we're getting things wrong. And as you go to other countries, you'll see similar numbers. Problem we've got is a lot of the systems are not designed to control. I think they're actually that cool you, looking at them sometimes. If we look at that system on your left, this red beast, that's a purpose-built, designed system here in New Zealand. in a trade training establishment for metal workers. It's designed to capture the fumes arising from brazing and from welding. But whoever designed it doesn't understand how these substances are actually released. When we test that system, we find it is effective 1 centimetre away down at the bottom. So you have to be welding hard up against that wall or brazing hard up against the wall for it to actually capture the contaminant. So there's a lot of things that we're missing there. So we have to understand how these contaminants move around in the air, how they behave in the air. And this becomes a common problem, as you will see as we walk through this. The other thing often not accounted for is the actual job that's done. Often we get designs done up, but when you speak to the designers, and they don't actually know what the job was. They were just designed for this, and they designed it, but they don't know how the people work and things like this. All those need to be taken into account. So one of the root causes we've got is that lack of understanding of contaminants and not actually knowing the jobs that are being done and the tasks. We go and look onto this system here. It's when we talk about HAVAC, often we talk about the air changes and things like this. When we're talking about LEV, we discuss capture velocities, duct velocities, exit velocities, as well as all our static pressures and other bits and pieces. So what's a capture velocity? Well, the capture velocity will actually capture the substance as it is released, entrain it into this and pull it into the system. If we look at this one on our left here, this is another purpose-built system. The fan is underrated for the job of the contaminant it's got to capture, in this case, diesel exhaust fume from fire engines. Whoever designed it, again, didn't understand the nature of the substance we are looking at. And when we look at many of the systems, one of the things we can do once it's properly designed, it's properly installed, is have it commissioned. The commissioning proof, it says what it does, what it says in the packet, that it will actually control, and it gives confidence to the workers and to the employers of the workplace that the system will entrain, will remove the contaminant and protect their workforce. Unfortunately, I've only seen one system in New Zealand that has actually been commissioned. And even that wasn't done correctly. The people that did the commissioning, and I saw this 2 weeks ago, went back to 1962 to get the standards. We've moved on a bit since then. And the stuff that was around in 1962 actually went out of date, late 1960s, early 1970s. But for some reason, people are still using it here for commissioning certain systems. And the commission, I say, is important. And you just have a look at a system, you can spot this one here immediately, it's not been done. There's telltale signs to say that it's been commissioned, it's missing. So this system's been designed, it's been installed, and that was it. The users are supposed to know how to use it, but they've not been trained in using this type of system. It's never been tested to say it will actually work. And the important thing around the commissioning is when the system's commissioned, as I say, the only ones I've seen here have been commissioned by the same people that have built it and installed it. That's bad work practice. Commissioning should always be done by another company, and then as independent check of your work as a quality control. And in this case, again, we can see the contaminant's not been considered. Diesel exhaust. Diesel exhaust is, for those that have worked with it, is a carcinogen. It's got a very low exposure level, and it's quite oily if you've got it, you get it on you, particularly when warm. And look at all the bends in this system. We've got right angles. Right angle joins going into one system into another, which will give us a lot of turbulence. And with this particular matter and the particulate in it and the wetness and oiliness of it means that it will start coating immediately on the inside and start building up. And wherever we've got corners there, our elbows, we are going to have settling out, which is going to cause more turbulence, which is going to cause more settling out, and eventually blockage. You can actually say that system there has been designed to fail at some point in its life. It's missing the hatches you'd expect for that particular contaminant around the elbows so they can be cleaned and maintained. So again, it's a lack of understanding of actually not just how the contaminant is acting outside of the system, but once it's inside, how will the contaminant behave with the particular airflows? And we don't know the airflows in that system. I was just passing it, and we saw this one because they have never been tested. So we don't even know if the substance has been entrained and is kept in the air and is actually going to be removed correctly from the work area. So you can see there's some common problems we're getting. I think we need to learn from these and come on to that. So, as I said, leading causes of death are things from carcinogen, respiratory, etc. diseases. One of the reasons we're getting high exposures is because the behavior and air of the contaminants is not being considered in the design. A lot of designers are not asking the right questions around the processes, tasks, or not talking to the workers. For an example, I met a designer. He came up with a lovely design. We had a look at it. And my question to him was, have you spoken to the workers? No. Have you ever spoken to the workers? Never. We don't need them. We got them in. And the first thing they said was, oh, this looks good. Can you now show us what it's going to look like? So he described it. And he says, we can't use it. We need daylight, and you're about to take away our daylight. And we can't do this task. Okay, so how about this? And then described how I was going to use it. Actually, no, we need that there for this reasons. So we got equipment in, we demonstrated what happened, he went, that won't work. We then came up with a system that might not be in the top, it's slightly down in the rankings, but it actually does work. And the workers liked it and they use it. When we design systems that are not suitable for the task, people will not use them. And we see quite a lot of that, systems gathering dust in the corner, even though they're brand new. And the reason for it is it's not suitable for the actual task. So why do we install it? Commissioning, extremely rare. In 15 years in New Zealand, I've only come across commissioning data twice, and never commissioning by a separate company. It's the same people that have designed, built, installed, that have done the commissioning, which makes you wonder, are the numbers satisfactory or not? And the other big issue we tend to come across, as I said, is lack of training in the systems. There's a system installed in the woodworking area. When we tested it, it had never been commissioned, but we went through the testing process and showed that it wasn't in training the contaminants, it was struggling to capture. And we were in excess of 10 times the workplace exposure standard for wood dust in the area. It wasn't being entrained in system, the dust, and it was settling out. And then I spoke with the operators. They actually admitted nobody had shown them how to use it correctly. So we spent about a morning playing around and eventually got it on a configuration that would work. Got it up and running. We retested the whole system. And this time we went down to less than 1% of the workplace exposure standard. So we've gone from 10 times above to less than 1% of the workplace exposure standard, which meant it's now under control. So the system was fine, but the workers have never known how to use it. And that again is a common issue we come across, is we're not commissioning, we're not demonstrating it's been used, we're not designing for the contaminants of the task. And when we install these systems, it's accepted that everybody knows how to use it, which they don't. They need to be trained, they need to be shown, they need the manuals, etc. around. So, talk a little bit about this. Number of lessons we need to think about. We talk about health and safety by design. It doesn't only apply to the actual workplace, safe moving around, a guarding of machinery, etc. It actually applies to things like local exhaust ventilation and the other control systems. We've got to have a focus not just on the safety, but actually on health. As we said, 750 to 900 each year dying from ill health related back to their occupations, to their jobs, and quite a few thousand get hospitalized. Now, if we can help reduce those burdens on the DHBs, on the families of the stresses and strains they face with their loved ones, getting these illnesses, and sometimes a slow, insidious death over years, then I think it's important that we make sure we apply these principles of health and safety by design to controls such as LEV, for a substance hazards to health. All LEV should be commissioned. Simple as that. Just because it's been designed and put in doesn't mean it will do the job. So it's got to be properly designed, and then we have to prove it to the workers. In many locations, we will find an LEV system that does work and is good, and we'll say to the workers, why you do not need to wear respirators. And they'll go, we'd rather do it, we don't trust it. That is not a good place to be. And these are the systems that you are installing, and people don't trust them. We've got to build that trust back up. And one of the ways we do that is by commissioning before it goes into full use, and actually prove that it does what it's supposed to do. Then we can persuade people to come out of these respirators. And that cuts costs to businesses and all sorts of other advantages. We need competencies. And this is an LEV. It's not just people like myself as a hygienist that needs to be competent in the thorough examination and testing of LEV systems. We need engineers to be fully competent. If you're going to work on an electrical system, you have to be an electrical engineer and you have to have the correct competencies. The same with things like gas. So why is it there's a belief that anybody can do an LEV system? It's a control, and we are probably killing more people each year than are dying from a gas exposure, from a faulty gas fitting or explosion, or from electrical issues. And yet we've got this belief that anybody can do it. As long as you can design a simple system, even a HVAC system, you can design an LEV system. As I said back at the beginning, HVAC, LEV, two different disciplines. And we need people who are going to commission the systems to be competent. They need to understand what's going on. You need to understand all the testing that has to be done and all the documentation that should be there. We should be able to rely on them for that information. And we have seen, let's just say, once in the past, not here in New Zealand, I hasten to add, but we have seen people lie, and we've caught them out very quickly, where they've done commissioning data and they've lied about the numbers at the back. And that's a very simple find. So we need people we can trust to do the commissioning. And as I said before, it should not be the company that's designed or installed it. It should be an independent company that comes in and does it, whether it be from engineering, hygienists, or whatever. But these people need to know what they're doing. They need to be fully competent in the subject. So when you think about systems, think of all the systems you may have been involved in or you have seen out there. Did you demonstrate to the PCBU and to the workers through thorough commissioning that the system is actually controlling the hazards arising and that system is effective? And if they look after it, as you tell them to in the guidebooks, in the manuals, etc., then that system will be there for another 40, 50, 60 years. And I have worked with systems that were built in the 1930s, and I was working with those systems right through to the early 2000s when we eventually replaced the buildings, and they had worked the whole life very effectively, very well, and nobody ever had to hold other PPE around it. So a well-designed system will last a very long time. So you probably gather what I'm going on about. Really, with any LEV system, we need people to be competent in the practical application of LEV. If you go back to my youth in this job, about nearly 40 years ago, the engineers used to train up, and you get some of them doing HVAC, and after doing their basic training in engineering, etc., they had a choice if they wanted to go into ventilation of either doing HVAC systems or LEV. They were both electives in the day. For some reason, LEV has dropped off the current curriculum for engineers. It's a separate discipline. And this is global, not just here in New Zealand. And it's something I believe that needs to be addressed. And we need people who are going to actually work with any part of it, from design right through to commissioning, etc., including the maintenance of and stuff. They need to be practical and apply that to the systems. We need a better understanding around physics, not just fluid dynamics or things going through the pipes, etc. We need to know how these things behave, the contaminants behave outside before we actually capture it. For instance, when we look at LEV and capture velocities, we have a range that can be used for the same substance. So it depends if it's wet, dry, what type of air is being released into. So there's a lot of background air, etc. we've got to overcome, and things like this. If you take a fume cabinet, which most of you will know of, when they're designed and they're built, if we go with the minimum 0.5 meters per second across the face with about 300 mil opening, that's fine. However, if you've got a lot of throughput traffic behind them of people passing, you actually need a high velocity. Otherwise, the chemicals actually get pulled back out of the fume cabinet. So we've got to understand the whole area and how the contaminant behaves in those areas and with the different conflicting airflows. We need to come up with some way, and I think guidance for everybody across the board, almost a criteria for best practice in LEV engineering that we can all follow, we can all understand. It can help us improve the systems out there and quickly catch out anything like the cowboys and stuff that they get involved sometimes with these. And I've got a very strong belief that we need better partnerships between the professional bodies. I understand that Engineering New Zealand have struck up a partnership with a New Zealand Institute of Safety Management, NZSSE. But there's other professional bodies out there, such as myself, my group with the occupational hygienists, we've got the occupational health nurses, we've got occupational medicine medicine with the physicians, and ergonomists, human factor groups. So there's a lot of groups out there. Everybody has a role to play, and engineering cuts across all our roles. So we might not be engineers, but we will have different skills and different things that we can provide that can help you improve what you provide to your clients out there. And I think this is an area we need to look at and develop. So, as I said way back at the start, we're killing a lot of people, and we're putting a lot of people into hospital, and unfortunately watching them degrade over time, because a lot of these things you do not recover from, you just slowly go downhill. Of the systems we see out in New Zealand, roughly 90% of what I've seen do not effectively control. As I say, we can apply this really globally around LEV. So what I want you to think about is look at things you have been involved with in the past, that if you've designed, you've manufactured, you supplied, you installed. Did you actually consider the workers who are going to use those systems? Is it something they can use? Will it actually control in the area? So the bottom thing for us is the workers, that when we do not control substances, it's the workers who are suffering the damage to their health. So the bottom root of any LEV system should always be, are we protecting the worker? So you can probably hear I'm quite passionate on this. When I see control systems, I want them to do what it says in the packet. I'd love to see the workers come out of a lot of the PPE that they currently wear, even when these controls are in place. I'd love to see systems that are going to last 50, 60 years with good maintenance. And I'd love to see the numbers of people that are dying from ill-related health or being injured through it, hospitalized, etc., reduced. And that will reduce the burdens not only on DHBs as well, but also the stresses on the families. So, to conclude, we have a need to provide LEV that is fit for purpose. We can demonstrate that it works, and for the future, it will continue to work effectively. That way, we will help between all of us to reduce that burden on the country of ill health and on the workers. Thanks for listening. And Joe.
Thank you very much, Derek. That was a very interesting presentation. And I hope everybody who was attending got something out of that. It's always good for our profession in general to hear opinions from outside of engineering. And this is one of the reasons why at the moment Engineering New Zealand is working through the process of becoming a member of HASANZ, so that we can have deeper and more systematic engagement with groups like the Occupational Hygiene Society and so on. So I'll run through the questions. Some of them I think I know what you'll answer, and some of the others might be quite big picture questions about the structure of contractual arrangements in New Zealand's various industries, but we'll see how we go. So first off,
and then you can help answer. You can help answer, Joe.
Oh, I don't know about that, Derek. I've got fairly strong opinions, but not necessarily constructive some of the time. So first off, why is commissioning not a standardised activity in New Zealand? Surely it's normally included in the sales package.
That's actually a very good question, and I do not know why it is not. But the workplaces where I do look at the systems, I always ask for the commissioning data, the logbooks, etc., and never get it. the companies go through the records and go, we don't have anything, Derek. So obviously, for some reason, this is not seen as part of the package. And I believe, as you obviously do, Emma, this should be part of the package.
Absolutely should be. Okay, is the initial training to use the system being dropped because of cost, which is a common problem elsewhere?
We don't actually know. I was at a meeting in the US at a conference, and we had a late night session on LEV and the situation. And then there's a lot of us from around the globe there. And the ACGIH, American Congress for the Governance of Industrial Hygiene, who are big into the LEV and write a lot of the manuals, they actually looked into this big style to find out why it had been dropped from the curriculum. They believe money was part of it, but they've never been able to prove that. It's, for some reason, it just got dropped off the thing very quietly at the back. And I think when we had the ones who had trained in this field still around, we never realized there's nothing coming behind them. We weren't getting the new generation coming through. And by the time they stopped, they retired, and we didn't have this new generation, and we started coming across more faults. That's when I think we woke up and went, something's gone wrong. And when we found out, yeah, nobody's training anymore.
Certainly wouldn't help. Do you have some recommendations on resources for those of us that want to learn more on LEV systems?
On that note, there's some very good resources. We're working on some at the moment, myself with Joe and a few others. So we'll build, I think, a good resource hub, and we'll get that out through your system, Joe, to your people. And of useful resources for LEV. There are lots around. UK's got stuff, America's got stuff, even Ireland's got some stuff. And so there is some good stuff out there in the market. And I think what we'll do is we'll build a little resource pack. And remember, there's also some basic information on WorkSafe New Zealand's website. So always visit that and see what the latest is, and things like that.
Mm-hmm. Somebody else further down has also pointed out that the ACGIH Industrial Ventilation Manual is a useful reference document, and I know that was the one you told me to go and read when I first started inquiring. So yeah, I mean, it's probably worth a look.
Yeah,
it's got most of the solutions already in it.
Yeah, and that's the thing. Why do we keep reinventing the wheel? It's like
a very good question.
It's like
engineers love custom designs, Derek.
I know, but it's like for vehicle exhaust fumes. You can buy it off the shelf. Really good systems that do what it says in the packet. But for some reason, as you say, engineers have to keep reinventing the wheel and designing their own.
So there's a good lesson. Don't do your own design. If there's already one, you can just buy it. Okay, some vent systems, e.g. spray booths, require certification and regular testing and maintenance. Should this regime be applied to other industrial vent systems?
Yes, is a very nice short answer on that one.
That's a simple one.
Yeah, I believe it should be done. I do believe, though, things like the spray booths need tweaking. I'm aware of the AS 4114, which talks about air changes. And unfortunately, most of the design on those booths, particularly in the paint mixing area, when we've tested them, if you lie flat on your face, so your head's less than half a meter off the floor, you don't need PPE. But if you're going to mix your paints on any higher than within 50 centimeters off the floor, you need full PPE because the air is heavily contaminated. And the reason for that one is the calculations. You do the calculations and yep, we achieve the standard because we've got the number of air changes required. What's not actually happening is all the air is not changing. And so we actually have a buildup of the chemical And when we speak to people about it, asking why all these vents at the bottom, it's because paint vapor is heavier, it's denser than air. Therefore, when you open a paint tin, it spills out over and it goes down sides, so you collect it at the bottom. Poppycock. That's a lack of understanding of how it works, because if that is true, why, when we open a tin of paint, do we get the smell of paint?
It's a fair point. I'm not going to argue the point with you.
We'll do it over a beer one day.
Yeah, well, no, I completely agree. So it would be a bit ridiculous for me to argue with you. Okay, are there standards that are recognised in New Zealand that can be applied to support LEV design? I think we've addressed that with one of the earlier questions.
Yes.
Yep. What do you see as the role of regulators, for example, WorkSafe in the LEV space going forward? They seem to be taking a greater interest in occupational hygiene and worker health in general.
I think it's supporting organisations like ourselves to develop systems. I think we are probably placed better, the engineers ourselves and other groups within HASANZ, etc., are placed better to actually build the systems for improving and using it as a good industry guides, etc. Because WorkSafe, through the regulations, etc., do have the piece around that systems have to be fit for purpose, and that the LEV control system, ventilation control systems, which LEV comes under, should be effective and should be tested on a regular basis to prove so. So all that's in the background. What we need them to do, we need to I believe we need to work in the background. We need to build the systems which can then be benchmarked against, and WorkSafe can pick up. Because at the moment, if WorkSafe went around picking up what we see, I don't think there's enough people in New Zealand who could actually sit down and actually solve the problems.
No. Well, yeah, we'll fix that though.
Oh, we'll get it sorted one day.
Yeah, it's also worth, I guess, pointing out that on the enforcement side, WorkSafe are certainly paying more attention to occupational health and chemical exposure stuff than certainly the old DOL and OSH ever did. There was a thing in the media yesterday, actually, a prosecution for a chemical exposure fatality, which I didn't look into the detail of, but you know, it does happen.
I know, speaking to occupational hygienists, colleagues of mine across the country, they're all extremely busy now. A lot of it is coming out of WorkSafe's actions and enforcements. And that's actually monitoring to see if the substances are under control in the workplace.
Yep. What gets measured gets managed, right?
That's it.
What are the standards and regulations we should follow in LEV design? Again, we've addressed that. Here's an interesting one. Where should one look to find a competent or qualified commissioning agent for industrial LEV?
$1 million question.
You, I guess.
I have enough on my plate at the moment as it is. That is one of the challenges we're going to have, is creating these. And this, again, is where I go back to the better cooperation between the societies and things to actually build some of these things and improve the training, etc. And if any of the universities are listening in on this today, if you do engineering, then please, by all means, approach and let's talk and let's start getting these people up and running, and let's look at courses and training. I believe with training, though, there needs to be more than just putting together a course and saying, here you go. I believe for a lot of areas, we need approved trainer providers. Because at the moment, in theory, if we created let's say an NZQA, then people could go out, you could have a secretary of a company teaching you. But I'd rather we've got hygienists and engineers working alongside each other doing these type of courses. So we've got input from people who actually know what they're talking about and can answer the questions. At the moment, there is some training around a testing of systems for thorough examination and testing. That includes the IP 601, International Proficiency Ticket 601. That's run through the British Occupational Hygiene Society and through SIBSES with the Institute of Local Exhaust Ventilation Engineers, ILEVE. And you can find some information about that from there. And we do some stuff around controls via the Hygiene Society on a course called the W505, which is the principles of control. And that includes quite a section on ventilation systems and LEV. But again, I believe what we need to do is build a system, get it, and maybe even have things like almost like a corgi card for the gas plumbers to say they're qualified, or electricians say they're qualified. Let's have similar for LEV. So you can say qualified to commission, qualified whatever, it's design, etc., etc. And actually have something that will give confidence to the end users that these people are competent.
So I guess the short answer is the same as in many industries at the moment. There's a very severe skills shortage.
Yes.
Across New Zealand.
Yep. If we've got people who believe they are, then please, by all means, get in touch with the engineers through Joe.
Yep.
And
yeah, the NZSSE would be more than happy to, serve as a conduit and a connector for companies to, make it clear that they are available to provide this service.
Yeah, and we've got some really good people out there, some really good engineering companies around. And there's no reason they couldn't have maybe a commissioning section within some of the big ones, things like this, that could go around and do the independent checking on each other and things.
Yep. Okay, what checks can I do on my current LEV system to check its effectiveness? We have portable LEV systems in place for brazing of copper and stainless steel. Okay.
It's basically make sure it's working. Have you serviced it recently, etc. Depends how you're doing the brazing, etc. Probably looking at top of my skull, probably about 5 meters a second across the face. That would normally actually catch a bit of paper. Believe it or not, is it quick and dirty? What I would do is I would call in for somebody to come in and test it for you. And there are people that can do that. You can find them on the HASANZ National Register, as is, or via a group like the New Zealand Occupational Hygiene Society. These are ones that we know are trained up in LEV systems. Okay. And I'm not sure, you don't have a list with the engineers of who's trained for LEV, do you?
Not yet, but beginning to think we probably should. I'll add it to my list. Okay, how would you go about installing ventilation for an open tank without enclosing the tank? Somebody wants some free advice?
Yeah, okay. That's a big question, because with the open tank, it depends what the substance is. So if you're looking at, say, solvents, they normally there'd be a cooling coil around it. Or you could have a push-pull system. It depends on the size of the tank. As to it could be lip ventilation. So there's a lot of different variations that could be done around an open tank, but you've got to understand the contaminant. So we need to know exactly what it was. We need to know how it's been released, and we need to know what's happening in the area around it. Then that would actually govern the design of the system for the tank.
So that one's probably too broad a question to be able to answer on.
It's too broad for here. This is where we need a correct design, and we need that engagement. And how are the people working around the open tank? Are they dipping things in, etc., etc.? Because that then again changes the design criteria.
Yeah, cool. Do you know of any consultants in New Zealand experienced in indoor shooting range extraction systems?
Right, I will pass on that one. Because I don't know of any particular ones. I've done a lot of indoor shooting ranges. myself, and one of the books we referred to earlier, we had information. So there's a lot of good stuff out there in the marketplace that we know works for indoor shooting ranges. It depends on the caliber. It depends how many rounds are being put in through the chambers in a one, and depends on the setup, with particularly down at the butt end where the targets are. But normally you look at a laminar flow, so it's blowing from behind the individuals, and it's been extracted out at the back through a filtered system. And that way the lead and air, which is what we're normally getting, is being blown away behind the person. That's in very, very simple terms. It's a bit more complex because it comes down to the building, the design of the building, and a few other bits and pieces, and there's layout. But that's the rough design, and there is information out there on the web you can get, because a lot of countries have done a lot of work, particularly in the militaries, around indoor ranges.
Excellent, thank you. And one last question at the moment: are there hybrid systems for fume, dust, and steam, for example, to apply in the steel industry?
Hybrid systems can be done. Fumes and dust are both particulate, so that's no great shakes. It depends on the actual dust that we're talking about. Same as on the fumes, because different ones will have different densities, etc., behave differently, and same with the dust. Steam's just moisture, so it's not a big factor in it. So yeah, there are systems that can deal with fume and dust quite easily. And I say, if you think of it, fumes are particulate.
Cool. All right then. Well, that is all of the questions we currently have. So once again, thank you very much, Derek. Plenty of time for all the questions there. That was good.
Yeah.
Sorry, what's it?
I was going to say, thanks for having me.
You're most welcome. Yeah, thank you very much for that. I hope everybody enjoyed the session. Keep an eye out for updates on the rest of this Lessons to be Learned series coming out of Engineering New Zealand. The next session is scheduled for the 7th of July and is facilitated by the Transportation Group. So save the date, 7th of July, same time, and more details will be coming in the next week or so. So once again, Derek, thank you very much. Thank you everyone for attending. And with that, we'll call the session done.